On May 28, I received an email informing me that I have been selected for the final round of IIT Madras internship program. Along with that email came a Notion page containing 3 assignment tasks. As I explored the option, one challenge immediately stood out. This was track 3 required building a full stack deepfake and digital forensic platform. It was by far the most technically demanding problem, and it was exactly why I chose it. Before writing a single line of code, I spent time researching modern forensic system, deepfake detection pipeline, and content authenticity framework. Once I had a clear understanding of the problem, I started by designing the complete user experience in Figma. Before explaining how systems work internally, let me first demonstrate the final product. This is Authenticity Scanner homepage. The platform is designed as multi-model forensic analytics system capable of analyzing text, PDF, images, video, and audio files. Each content type follows its own forensic pipeline while sharing a common report and explanatory framework. Let's begin the text analysis. I'll paste a sample text generated by ChatGPT and initiate the scan. Once the analysis starts, the system evaluates the text using multiple AI detection models. After processing, it returns an overall probability score through the supporting forensic indicator. The circular score visualized represents the final confidence level. Below that, the explainable AI section generates a human-readable explanation describing exactly why the content appears synthetic. Instead of only displaying a percentage, the system explains the reason behind the decision. Next to it, the forensic breakdown panel displays the individual signal that contribute to this final score. Now let's move to PDF analysis. When a PDF is uploaded, it analyzes the document structure, examines embedded image, processes textual context, and combine all the findings into a single forensic report. The output includes a consolidated authenticity score, a summary of findings, and an explanation of any suspicious pattern detected. Next is image forensics. Here I am uploading a manipulated image. The system generates a forensic heat map that highlights suspicious region within the image. These regions are identified through analysis of metadata anomaly, synthetic noise pattern, visual inconsistency, and structural artifact commonly associated with AI-generated image. Now let's talk about system architecture. Frontend is built using Next.js 16 and React 19 and is deployed on Vercel. The backend is a separate Python fast API service running on UVCon. All machine learning model inference is performed through Hugging Face API. One challenge quickly emerged during development. Large language model and visual model often experience cold start. If the frontend waited synchronously for model response, user could encounter gateway timeout and poor experience. To solve this, I implemented an asynchronous job pooling architecture. When a user submits a content, the frontend sends a post request to Fast API backend. The backend immediately validates the request and returns to 202 accepted response together with a unique job ID. At this point, the backend tasks began executing the forensic pipeline. The analysis run independent generates the explanation report and stores the resulting JSON output. Meanwhile, the frontend continuously pulls the request input every 1.2 seconds using the job ID. Once the analysis is complete, the result is retrieved and displayed to user. Now let's talk about engineering the forensic pipe. The first text detector I implemented was widely using Robatra-based OpenAI detector. Revealed major limitation when processing large document. Input exceeding 514 tokens triggered tensor size mismatch error, resulting in HTTP 400 failure. To solve this problem, I designed a dual model weight assemble architecture. To prevent memory and tokenization issue, I implemented a dynamic chunking algorithm that displayed large, approximately 1400 character segment before processing. The final score is generated by combining both model output. For image analysis, I initially relied on traditional forensic technique. This includes fast Fourier transformation, error level analysis, and Laplacian noise volume. While this model performs reasonably well on controlled dataset, they generate unacceptable false positive rate on compared to real-world data. The final architecture through combined classical forensic with modern deep learning. At a core is a Cyclip2 vision transformer known as Deepfake Detect Cyclip2. For the multi-model PDF processing, backend uses PyMuPDF to unpack the PDF document structure. The first 3 pages are rendered for visual forensic analysis. The textual content is extracted and passed through the text return. Talk about the final deployment phase. The final deployment consists of 2 independent services. The Next.js frontend runs on Vercel and handles rendering, user interaction, and client-side PDF export functionality. The Fast API backend manages a multi-thread forensic pipeline and machine learning inference workflow. I hope you liked our project. Thank you for watching.